Also feel free to ask any questions during my talk or to disagree with what I say. And what's the problem? So we look at the so-called non-parametric regression model. So this is we have n training samples, and we believe so they're generated from this model. So the responses, there's an unknown function f0, the regression function, and these xi's, they're also drawn IID from some distribution, and on top of that, the responses have this measurement errors that we assume to be a standard normal, and non-parametric least squares. So it means we compute the empirical risk minimizer over some function class calligraphic f in order to recover this unknown function f0 from the data. Okay, so we have yesterday and today there were already some talks on covariate shift. So during the training time, we assume that the xi's, they're drawn IID from the distribution, say, px. But we are interested in the scenario where during the test time, actually we want to evaluate it under a different distribution, say qx. And throughout my talk, I will always assume that px and qx, they have the back densities, and then I drop the index x, so they will be called little p and little q. Good. So what's the thing now? If we want to understand how the least squares, the non-parametric least squares estimator performs under covariate shift, then the main obstacle is the current techniques from statistical learning theory, because this typically gives us convergence rates of the least squares estimator that are with respect to the density p. And so this is very hard here to get something for, if we want to evaluate it under a different density q. And so that this is the natural object is very, I mean, the way the least squares is set up somehow, this is the noise level. If you take expectation here, that's the noise level plus that, okay? So for fixed function f here. So that's somehow the natural loss, and the statistical learning theory that tells us something about that. And the question is now, how can we say something about rates of convergence for that object? And there's one exception, is the case where this function class f is comes from some class of shape constraints. Then in some of these cases, you can say something much more explicit about the least squares estimator, and then you can work out also even pointwise results and distributional results. But I don't want to look at those ones, because the shape constraints, they typically put very strong form of regularizing, like they induce a lot of regularizations in the sense that, for instance, if you assume you minimize over monotone functions, then you can't allow that the reconstruction wiggles around us. So I'm really interested in the case where we have something not related to shape constraints. Okay. So, and what we do here is just looking at functions that are Lipschitz with Lipschitz constant 1 in one dimension. And so under the measure p, the convergence rate is, I mean, the classical non-parametric convergence rate is the 2 beta over 2 beta plus d, where beta is the smoothness and d the dimension. So here the smoothness is 1 and the dimension is 1. So 2 beta over 2 beta plus 1, that becomes n to the minus 2/3. So that's the convergence rate that we obtain under the source distribution p. But then the question is, like, if q is, for instance, very different from p, when does that deteriorate? And which type of convergence rates can we expect in this case? So why do we pick Lipschitz functions? So there are two reasons. The first one, and I come back to that later in my talk. So otherwise, it's mathematically very hard. So we found that to be something somehow still mathematically tractable. And the second thing is it's somehow related to value networks, because value networks, they also generate piecewise linear functions. And in the one-dimensional case, if you take a shallow network, somehow you can, with n hidden units, you can represent all piecewise linear functions with, say, n+1 pieces. So what you can show is that if you take instead the function class of value networks, if you constrain that to these value networks, they only can spit out Lipschitz 1 functions, and you take enough hidden units, then all the empirical risk minimizers are contained in the empirical risk minimizers, because over the Lipschitz space, because you can see that if you have an empirical risk minimizer that is not piecewise linear, then you can replace it by something piecewise linear, and you can only make the least squares loss smaller. So that's basically the argument here. Okay, so that somehow means we get maybe some sort of insights about how that works if we constrain the class of neural networks in a specific form that they can't have arbitrary Lipschitz constants, but this is contained in some ball here set to be 1. Okay, so now before I come to the formal statement, this is a bit the scenario, right? So here I have drawn something where you see the design distribution is concentrated on the right, and there are very few covariates that lie on the left side. And if we have very few covariates, so we have very few observations on the left side. And that means in this region, we expect also that the least squares estimator will be somehow worse. And we really have to specify by how much, because if we have later a new target distribution that puts a lot of mass on the left side, then we integrate over that. And then this will basically dominate what the rate will be, right? So we have now to be really to study like what is the local rate here on the left side, in particular the cases where we have low density, low design density. So that's the tricky bit. Okay, so what's the result here? So the result is the local rate is given by an equation. And so we can show that this equation here, where you take the design density and you look at every point x on how much mass it gives to an interval of length 2tn around x, centered at x. And then you multiply that with tn x squared, and you equate it to log n over n. So that has a unique solution tn. So that will be the local convergence rate that we can prove for this least squares estimator over 1 Lipschitz functions. And we also have to assume a doubling property of the design distribution, the source distribution. So that means if you have an interval with radius, so the length 4 eta centered at x, so the probability given to that should be at most a constant times the probability of an interval with length 2 eta. And this constant is somehow fixed and does not depend on x or eta. And that's seems to be a harmless condition, but it rules out certain cases that we still would like to discuss, because it's if you have somewhere 0 density, right? So then if you have a fixed interval of 0 density, that can't happen, because then the doubling property would mean somehow you would have density 0 everywhere, and that's impossible. So we also replace it by a more local version of this doubling property, which allows us to be a bit, gives us a bit more slack, but I didn't put it here on the slide. And under this condition, so what we can show now is that the least squares estimator achieves the rate tn uniformly over, right? Everything here is always on 0, 1, so uniformly over 0, 1. And that's also uniform over the true function being, so it can't be actually on the boundary, it can't be a Lipschitz 1 function, but it can be anything which is like a bit smaller than, like a radius bit smaller than 1. It's also uniform, and I didn't put that on the slide, it's also uniform over a certain large class of design distributions, basically all of them that satisfy the doubling property with the same d. Okay, so that's, I didn't put the soup here as well, but it's also, there's some uniformity with respect to that. Martin, yes, yeah.
Just a question, like, having something called 1,000, but I don't see in the theorem where it's actually going to sort of appear. Is it in the limit, like the rate at which it goes to 0?
That's right, yeah. So that was somehow we didn't track the dependence on the yeah.
And can you give some examples, actual examples where it holds or does not hold?
Like the doubling?
Yeah.
Yeah, I think the best case is somehow, I mean, if the density is bounded away from 0, right? So then it's always fine, right? So then it's okay. That's okay. The thing really kicks in if you have these low density regimes. The most extreme case is if you have density 0 on a fixed interval, then doubling cannot hold because it's somehow violated. So suppose it would have density 0 somewhere, could then also the density, it has to be density 0 on a interval of twice the length, and then and so on, and so you can show that. And so it's really subtle in the regime where you're close to 0. So later, actually, we also allow this px to depend on the n. So I mentioned that we also have this result uniformly over px, such that we can also look at sequences of design distributions, because then we can let the density tend to 0 with the sample size, and then we can understand somehow the behavior in this low density regime much better. Okay, so, and then we can also show that this Tn is the optimal rate. And so if you have a local rate that changes with x, it's not so clear what that means. Here, what it means is that we can take the constant to be, the constant capital K to be 1/12, and then put here the infimum over all estimators, not only the least squares, but over all estimators. And then we can show that, and that will not converge to 0 anymore. Right? So it's quite a concrete result. And so in this sense, it's the optimal local rate. Good. So now the main work in this project goes into how to prove this result. The first case, yeah. Mm-hmm. Yes, yeah. So then you could take here a 1/n if you want. Yeah. So that also comes back in the proof. So the standard proof. So first, I want to convince you that the standard statistical learning approach won't work here, because so what do you typically do is if you say, okay, so I have this as the empirical risk minimizer, and suppose my true function is also in this function class, then the first step is typically to derive what is called this basic inequality. And then on the left side of this basic inequality, we get something that already looks like the prediction error under the source distribution. And the right-hand side typically bounded with empirical process theory. And there's nothing we can really do here to get rid of this thing or introduce a different distribution here, right? Because this was a global criterion. Somehow we just get this inequality in this form. So there's nothing we can do about that. That's let's say the problem. But Samuel, you want to?
Yeah, just the result on the last page.
Yeah.
So the soup, maybe you said that earlier, the soup is over not just all functions, but over all distributions. I'm trying to understand why.
So there's another soup here, which I didn't put here because I don't want to put too many technicalities, but there's another soup over px that basically satisfy the doubling condition with the same constant capital D. So that is here, such that we later can also take sequences of source distributions.
So I guess the connection I'm not getting is there was a connection to transfer learning, which I've missed.
Yeah. Okay. So that comes. Okay. So first we try to understand these local rates, and once we have the local rates, basically what we can do, maybe I can skip a bit forward. So what we can do is once we have the local rates, and now we are interested in evaluating this under Q, right? We know that this is bounded by Tnx squared, and we can just integrate with respect to Q, and then we can say how the least squares STB. So therefore we need somehow the local behavior here. Okay, sure. Good point. Okay, so the first thing, okay, so that's the standard say statistical learning approach won't work here. So what we do instead is we say, okay, let's try to prove this by contradiction. Okay, we assume that somewhere on the interval 0, 1, we can find an x star, right? Well, this is somehow implied by the contradiction argument, that there's somewhere an x star such that, okay, before we had the absolute values, but assume just without the absolute values that this is larger than a large constant k times the local rate, right? So that's the start of the argument. And now I made a drawing here. I hope you can see a bit. What I plot here is the green function is the difference here of the estimator minus the true function f naught. And by assumption, it will cross this line, which is later what we want to show to be the local rate. So because by contradiction somewhere now it's above this line. Okay, so we call that point x star. And the idea is now that we can, at this point x star, we can find another function g. And this function has also to lie in the same space. It has also to be Lipschitz 1 function that lies below the green function. Because if it lies below the green function, and if we know that somewhere in this area we have at least one data point, then we also know that the least squares criterion will be smaller for g than for f hat. And that means we found a contradiction to the fact that f hat n is a least squares estimator because g has a strictly smaller least squares loss. Okay, so that's the idea. And so how large do we have this area to be? So it has to contain one data point, and this is also related to Kai-Shen's question earlier. So you want that somehow one data point falls into that, and now there are Lipschitz functions, so you can basically work it out, and that's also where this local rate comes from. That you then would have here that this local rate description, which I put here in blue, so that this would hold with the constant 1 over n. But now we have this uniformity that we also want to be uniform over 0, 1. So we have to do that for lots of like little intervals. And that gives us in the end the log factor. And that's because we have the lower bound that also shows this is unavoidable if we take this. So we need that here's a point with very high probability, right? Okay, so now that seems all very easy, right? So you just construct the G and that's it. But the issue is to construct the G. Okay, so why is that so hard? Well, because the f hat typically will lie at the least squares estimator will lie at the boundary of the space. So if you had the boundary of your space, so this is a function that is locally almost everywhere has Lipschitz constant 1, then it's very hard to put a perturbation because then that will move you out of the Lipschitz 1 space, right? It will give you maybe Lipschitz 1 plus delta Roche, right? So it's a bit more. And so that's very hard, therefore, to find this G. And here we use that the argument here is that the true function is actually in Lipschitz 1 minus delta, and delta is positive. So if the true function is in Lipschitz 1 minus delta, that means that the f hat cannot always go up with Lipschitz constant 1, because it would go up with Lipschitz constant 1 and it would be somewhere very far away from the f naught, and that would give you a contradiction as well. So somewhere it has to go down again, and that is exactly the moment when you can put the perturbation this G. Okay, so to make sure that the perturbation G is still in the function space Lipschitz 1. And so this is a very difficult construction. Actually, it's harder than what I plotted here because we couldn't manage to get the perturbation at x star, but there's somehow a point close to x star where you can put your perturbation. And so why do we need the doubling property? Because we don't really understand very well where the black curve and the green curve, where they will merge, like where these points are. And we just have upper and lower bounds, but we need to be sure that they both have basically the same behavior in terms of how many data points fall into them. So that's where the doubling property kicks in. Okay, so that's the proof idea. Some questions on that? Oh, you have a question, right? Yeah. Yeah. Mm-hmm.
Like, can you construct functions that are actually on the boundary for which you have the lower bound, or is the lower bound also only for the interior?
So if the lower bound, if you restrict that for Lipschitz 1 instead.
Yeah.
So then you make the space larger, so that should always hold, right? So because it's a lower bound. So.
What I'm saying is, if I have a function which is exactly on the boundary.
So okay, so
yeah, it's not that it has Lipschitz semi-norm.
So if it's exactly at the boundary, then
because the rate should be faster on the boundary, right?
I see. So if you just know it's everywhere exactly Lipschitz, like it's a piecewise linear function, and
Sure. Yeah.
and the linear pieces all have slope 1. That's I think what you think of. We haven't studied that.
And then the other question I had is, in this upper bound, can I take delta to 0 with n?
Yeah, that's a good question. We work with a fixed delta, but this is also one of the open problems actually to take it to 0. What happens then? Yeah. So I would really be interested in this, in the behavior then, and maybe other effects can occur in that regime. Thanks for your questions. Okay, so here's a bit on this convergence rate because it's implicit. So if the density is bounded away from 0, then this Tn will be the rate log n over n. So basically n to the 1/3. So basically n to the minus 1/3. But very different behavior can occur if the Tn is close to 0, and therefore that these things don't get somehow buried into constants. We make also the source distribution depend on the n. Okay, so and it's a nice observation that the least squares estimator, you don't need to do any. I mean, although it optimizes a global criterion, it also does locally very well. Yeah, so also in the sort of weighted subnorm distance, which is also stronger than L2, it still performs at the with the optimal convergence rate. And that's also different to kernel smoothing, because with kernel smoothing, if you pick a fixed bandwidth, you can't really adapt to the difference in the design distribution. So you would at least have somehow an estimator for your design density and stick that into your bandwidth choice in order to achieve the same behavior. But the least squares estimator doesn't need that. Of course, it comes with the thing that you have to put the radius to be 1. Okay. So how many minutes do I have that? Okay, perfect. Yeah, so I can. Yeah. Okay. Mm-hmm.
So back to when delta.
Yeah.
So you're going over the class of 1 minus delta Lipschitz.
Yeah.
Is that the Lipschitz constant?
Yeah, that's the Lipschitz constant of the true regression function. Say for simplicity, the true regression function has Lipschitz constant 1/2, but you take the least squares estimator over all 1 Lipschitz function. So you look for a bit larger class. Yeah. Okay. Mm-hmm. Yeah. Thanks. Okay, so here's now finally someone asked about what has this to do with covariate shift. This is one example. Now you can give some result. For instance, here in this result, we assume that the smoothness of the density is between 0 and 2, and the densities, now I said we make them n-dependent to make all this visible. So if the densities have to be somehow bounded away by 0 by the sequence n to the minus beta over 3 plus beta. And then in this case, one can show that this local rate squared is that. So it's log n over n pn of x to the 2/3. And if we then just stick that into this first displayed inequality, then we see that the prediction error under the target distribution, which is given by the right-hand side. So you see that it in this case will deteriorate. So we said without under the source distribution, we will have the rate n to the minus 2/3. Now there's always some log term that comes in because of the thing that we did uniform rates. So that's okay. Maybe ignore that a bit. And then we also have this term, but that also will go to infinity as Pn goes to 0, right? So that we pay a price of that the source distribution at low density region, and the target distribution might have say its Q is equal to 1 or so. Then we will lose in terms of convergence rate. Here's another example where we say, okay, so the source density is a density that has very little mass on near zero. So that's here the densities are plotted here. And the target density, the Q, is just a uniform distribution. So that means somehow we have few observations on the left side of our plot, with what I showed earlier. And but we, under the target, we are likely or equally likely to see an observation on the whole interval 0, 1, because it's the uniform distribution. So what happens now with the prediction error? First of all, we can work out what this local rate is. So you see in the regime where we are bounded away from 0, it's the n to the minus 1/3. So if x is larger than a half, it's n to the minus 1/3 up to this log factor. But then if you get closer to 0 with the x, where you have little, few observations, that's a low density, then this rate will increase, but it will somehow stop at some point, so it will not increase forever. So the worst case is this log n over n to the 1 over alpha plus 3. So that's what happens on the left side of your plot. Now, if you stick that into that, so you can now evaluate, if you take as target density the uniform, we can evaluate what does that give in terms of convergence rate. And then you see, in this case, if the alpha, right, the alpha says like how little mass you have on the left side of your plot, if that is larger than 3/2, then we lose in terms of convergence rate. Yeah? So before, although there is a low density region on the left, and under the target distribution, we see like a uniform distribution. So there is some discrepancy, but this doesn't really kick in because it's on a small area. But if this becomes too extreme, and here this is driven by this alpha parameter, so if alpha is exceeding 3/2, then you suddenly lose in terms of convergence rate. There's also another paper by Rees and Martin, and where they study another area Watson estimator, and they have a different framework, but we try to work it out. What in this scenario would happen, and I think if we did it correctly, then I think it will work in their scenario. It will happen in their setting. It will the rate of convergence will change for alpha equals 1 already, and that has to do with this, with what I mentioned before. So the kernel estimation, kernel smoothing, it doesn't have with a fixed bandwidth. Then you can't really do this local adaptation, so you can't get the local rates. So it's a bit worse on the left side, and that makes the rate to deteriorate already earlier. And also the analysis, I should say the analysis is different because not a Watson estimator, you have somehow an expression on how it looks, and we have to work with this implicit formulation of this, that it's an empirical risk minimizer over Lipschitz one functions. Now, to finish my talk, I want to mention the case we have also a few samples from the target distribution. And so we also get a Q this now here. So we have another M samples from the target, in total N plus M samples. And now we have, we can associate to each of these two subsamples, under the source and the target, we can associate a corresponding local rate, TNP and TMQ, so they get now index P and Q to indicate the dependence on the source and the target. And so what we can do now is we can come up with a combined estimator. And the combined estimator, so we could either do, of course, we could say, let's take a least squares estimator over the full data set. And that in principle would give us a good estimator. But we rather think here about a different situation where, you know, someone has trained, say, a model, and what we get to see is the least squares estimator from the first sample with the sample size n from the source distribution. And so we can only work with the least squares estimator, not with the full data set. So what to do then? Well, the proposal is we know the local rates. So and at every point x, we look which of these estimators, and the one from the source distribution or the one from the target distribution, has the smaller local rate. And then that's what we take in our combined estimator as the estimate at this point. So that gives an additional difficulty because the local rates also depend on the design distributions, and we have to estimate them from the data. So they get now Tn hat P and Tm hat Q. And so how do we do that? Is basically we just replace these, they were given by an equation, and the equation involves the distribution, and we replace it by the empirical distribution. And then basically that gives us the empirical estimates for the local rates. And so if we do that, we only need indeed the least squares estimator from the first sample. I think that's an important thing. And for the estimation of the Tn hat, we don't need the responses, right? It's only about the design distribution. So we only need the covariates. If someone gives us a few covariates also from the first sample, we should be able to do that because it's somehow, we just need consistency for that part. Okay, now if we look at this combined estimator, then we have also a theorem that says that this combined estimator will achieve the rate, which is now the minimum of the two individual rates, which is somehow natural that this will occur as the rate. And this is also in the same sense as before is the optimal local rate in the minimax sense. Okay, so that also shows us, which is somehow also intuitively clear, that even if you have a few samples from your target distribution, that won't necessarily increase the convergence rate because it doesn't help maybe really to, helps maybe with the constant, but not really with the rate. And here we have one example where we show that in a bit more precise way. So think about the same scenario as before. So the source distribution has a density that goes to 0 at 0, and so that's driven by the parameter alpha, and the target density is uniform. And now we look into the regime where under the source distribution we lose in terms of convergence rate, and that happened if the alpha was larger than 3/2, right? So that was the thing we worked out earlier. So that's the interesting regime where we suddenly just working with the source distribution won't get the n to the minus 2/3 rate anymore. And now what we can show is that if we get enough samples from the target distribution, so that's this inequality that says m has to be of a larger order than n to the 3/3 plus alpha, then we get as a convergence rate something that is an interplay between the m and the n. So the m is the number of samples from the target, and the n is the sample size from the source. So if m is equal to n, well, then we get the n to the minus 2/3 rate back, which is somehow clear because then it's basically just working with the charted domain would be sufficient. If we have less than n to the 3/3 plus alpha target data, then we don't improve on the rate any base. So we could also throw away the target data because it's in terms of convergence rate, because it's not strong enough to improve the rate in this regime. So we can understand a bit the interplay on how many data points we need. Now, here's some extensions. Okay, so a few minutes. One thing that really bothers me is when I started this, I thought, well, we can do general smoothness and general dimension. And it's also clear what the local rate is in this case. Well, we couldn't work it out. So the thing is that we really needed in our function class, the maximum and the minimum is also contained in the function class. So that really helps us to work, like construct this perturbation that I showed for the local rates. And that's not the case if you go beyond smoothness 1. And then, yeah, we tried all sorts of things to smooth it on the boundaries, and so it just didn't work. And so that's a main obstacle that remains unsolved. So I was really hoping to, and we tried a lot, and we couldn't solve it. Maybe someone has a great idea for doing that. Another thing is, of course, I made this link to value networks, shallow value networks, and so it would be interesting to see a bit also the local, whether one can say something about the local rates of, say, shallow value networks. And another thing which also Reese was mentioning earlier is what happens if the function that you want to learn is exactly has the same Lipschitz constant as the Lipschitz constant that you use for your least squares estimator, and then everything seems to change. And definitely there's some interesting phenomena occurring there. And with this, I want to close here. So what we did is we derived these optimal local rates, Tn for the least squares estimator taken over all Lipschitz 1 functions. I think the main novelty is the proof, how to derive the proof, because you have to go somehow beyond the standard statistical learning framework. And then we can insert that in order to get convergence rates for the least squares estimator under covariate shift. You always have this log n, which is a bit annoying because of the uniformity that we had before. And then we also covered the case where there's a second sample and show that the convergence rate in this case is the minimum of the individual local convergence rate. And we constructed an estimator that achieves that rate based on the least squares estimators of the individual samples. And I think in principle, this technique, and so there are probably many cases that one still can do to extend it. With this, thanks for your attention.
We have time for a few questions. Yeah, we have a couple minutes.
If we don't assume X to be bounded, does what happen?
It's a good point, yeah. So if we haven't really looked into this case, but that might be one very good extension. I don't know. But what would you think? What will happen? So maybe you're the expert. Yeah. So the boundedness, I think it's mainly relevant for. Say, let's do the first case. You have a growing interval. And so you think again about a sequence of problems. You let the interval grow to infinity at a polynomial rate and the sample size. And in this case, I don't think you will lose. Like the same rate will, the same result will apply with the same rates. Because you can all put that into the log n factor. And then if you have something that is distributed over the whole real line, I wouldn't know how to extend that case.
Yeah, can I ask one quick question? Actually, I'll give you so the risk in the end when you're bounding the target risk, this is still the integrated L2 square risk, right? And so presumably that's why you were bounding the pointwise risk on the source, right? But bounding the pointwise risk on the source seems to force you to introduce these doubling assumptions, right? And so it makes me wonder if you're caring about the target risk just in the integrated square loss, squared error on the target. Maybe you didn't need to bound pointwise everywhere the error of the right.
That might be another thing to do, yeah. So instead of here going directly. Instead of doing that uniformly, going directly to the integrated version. But I do believe that we still need the doubling condition, and that has to do with the way we the proof will work. So we don't. There's always.
I mean, for the ERM maybe, but generally, I mean, if you just even in previous work on covariate shift, non-parametric covariate shift, you don't need the doubling condition, right? Necessarily. But I think that I talked to you about some of those offline. You had a question?
I had a follow-up question regarding this doubling argument. So, I mean, it seems like these two things are decoupled in the covariate shift result which you have. Like you are assuming the doubling argument for the source and the target distributions separately. I assume that's the case.
Yeah, just for the source, right?
Just for the source. So what happens like if you have a doubling argument from the source to the target? Right? Like these kind of arguments are used in off-policy literature.
Okay. Yeah. So indeed, what you say is true. I mean, we decouple the problem by just looking at the these first the pointwise ones, and then we are just left with something on P, and then later we just once we have the pointwise without be integrated over Q, and so you want to couple them. Maybe we should talk about that. Maybe I can learn from you how to do it.
Yeah. So I think maybe one quick related comment to what Samri was asking about. I mean, the one benefit of your result is that you can have a guarantee for any Q, right? Because you have pointwise rates. So, Samari's approach would give you something for, a fixed Q. So my question is actually, so instead of looking at, let's say, pointwise rates, you could look at rates, say, over intervals or, subsets of the domain. I'm wondering if your, I'm wondering if your proof strategy would work for kind of something intermediate between pointwise and integrated risks.
Yeah, I think the pointwise one is quite convenient actually, because from the way we construct the perturbation. So if you would say, okay, so you want to do that over an interval, I wouldn't know how to construct perturbations in this case.
So it sounds like we should sit down and have some discussions later. That could be nice. So thanks everybody again. Let's thank Johannes one more time, please.